when we talk of the control systems, right? Now we have already seen that root locus is a tool which graphically displays the information about the location of closed loop poles, and uh, this is obtained from the knowledge of location of open loop poles and zeros, with the parameter gain k, which is varied from 0 to infinity, okay, as we have seen in the previous session, right? Now like if I want to again see that the gain adjustment is not giving me the transient response as specified, there is need of compensation, right? All of you know this, you might have seen in the videos, right? Now let us see that how we'll be designing the compensator using the root locus, right? So we can have lag compensator design, we can have lead compensator design, and then we'll do a problem based on both, right? So shall we directly start with a problem? And meanwhile, if you have any doubts in between regarding the concepts or how we are reaching there, you can ask me right then and there. Okay. So let
Sure.
us start with a simple example here. Suppose we have a unity feedback system where GS is equal to K by S plus 7. Okay. And you have to design, the objectives are, you have to design a lag compensator w- where the peak overshoot should be less than equal to 15%. And the second design objective is that the steady state error for unit ramp input is to improve by factor of 20. Got it? Okay. So how do we start this problem? How do we approach it for designing the lag compensator? Okay. So first of all, this system which is given with a unity feedback is termed as your um, uncompensated system, right? There is no compensation here. So here unity feedback means HS is equal to 1. So first step is, I'm just telling the steps and then we are doing one by one, right? So what is the step one? We have to sketch the root locus for this. Root locus for this uncompensated system, right? So shall we do it quickly? How to plot? It will be again a revision also that we have done in the previous class. Yes.
Sure, ma'am.
Okay. So can you tell me the steps quickly one by one? Yash is here today. No. Okay. Just we have to identify here the number of poles and zeros. So how many zeros are here? 0. And how many poles are there? 2.
Two.
At s equals to 0 and s equals minus 7. Right? Okay.
Yeah.
So what is step number 2 here? Then we have to draw the root locus at S plane, right? So let me draw here the S plane. Okay. Then I have a pole at 0 and I have a pole at say minus 7. and this is my minus infinity, right? Then how do we see that where my root locus is going to lie? Last time I have told you that root locus originates from poles, right? So what I have to do, I have to see from 0 towards the right hand side, and this is the right hand side, and this is the left hand side of the S plane. Okay, so is there any like zeros or poles here? No. So no poles and zeros here. Now I move towards -7 and see whether there is any uh, poles or zeros here. Yes, that
Yep.
is one pole and odd number, right? I told you the concept of odd and even to locate it, right? If I see from 0, 0, so 0 we can say it's even, and if I see at -7 there is one pole here, so my root locus is going to lie between this, right?
Yep.
So I'll mark this. I'll make it thick a little bit, right? Now come to minus infinity and see we have two poles. So again, from minus infinity to -7, there won't be any root locus branches, right?
Yep.
Now you know that the root locus originates from the pole. So here there will be a branch that will be originating from 0, and another branch that will be originating from -7, right? So now, since these two branches are coming towards each other, what we'll get? There will be a break away point. Okay.
Yeah.
Yes.
Yes, ma'am.
And this direction, this will be going towards, this breakaway point will be going towards infinity. They are coming towards each other and they'll be breaking away and going towards infinity, right? So the direction of the breakaway point, okay, this, sorry, direction of infinity from the breakaway point is told by the angle of asymptote that we have discussed in the previous class. And the angle of asymptote is drawn by knowing the centroid, right? We need to have centroid in order to know that from where we have to draw the angle of asymptotes. And angle of asymptotes are required for the direction of infinity, which will be telling the root locus, the direction of the root locus. Okay, so next what we'll find out, tell me? We'll be finding out the centroid, right? So centroid is represented as a sigma, and it is given by summation of real parts of poles minus summation of real part of zeros divided by p minus z. So how much it is going to be? Real parts of poles is 0 minus 7 minus 0 divided by 2, right? Here real parts of poles we have to take the algebraic sum, always remember that. So this comes out to be minus 3.5. So where centroid going to lie? Centroid is going to lie at minus, say,
Midpoint.
yeah, minus 3.5, somewhere here. Got it up till here, right?
Yep.
Next is uh, what we have to do. Once we have drawn the root locus, we have found the centroid. Then next is we have to find out the angle of asymptotes, right? So the angle of asymptotes, that is theta, that is given as 2q plus 1 divided by p minus z into 180 degree, and q is given as 0, 1 up till p minus z minus 1, right? Got it? So now if I put here p as 2, z as 0, minus 1, this will be 1, right? So I'll be taking two values here, 0 and 1. Okay. So what will be the value of theta 1? If I put 0 here, that will be 1 by 2 into 180, that will be 90 degree. And the next value will be again here 3 divided by 2 into 180, that will give me 270 degree, right? Clear up till here? So I have found out the centroid. I have calculated the angle of asymptotes also. Next is my breakaway point that I have to find out. Okay. So breakaway point is calculated by differentiating k with respect to s and then equating it equal to 0. Right. So can I find out this k? And from where I'll find out this? By the characteristic equation. Characteristic equation is 1 plus gs hs equals to 0. So which gives us 1 plus what is that? Gs k by s plus 7, and since it is a unity feedback system, hs is 1, equating this equal to 0. So s into s plus 7 plus k is equal to 0, and I'll get k equals minus s plus 7, right? Now differentiate this, see what you'll get. D by ds of minus s square minus 7s is equal to 0. So this will be 2s minus 7. This is negative, right? Equals to 0. So s is 7 by minus 2, that is minus 3.5. So you can see here that the centroid, that is your minus 3.5, as well as your breakaway point also comes at minus 3.5, right? Is it clear up till here?
Yes, ma'am.
Okay. Now see,
Yes.
let us complete the root locus
I think
without any.
Neetu has a question, ma'am.
Yes, yes, yes.
Yes, ma'am. In
Hmm.
the while finding the angle of
Asymptotes.
uh,
Hmm.
uh, won't we have plus minus symbol in the front and
Plus minus
symbol in the front, and
here.
isn't it
Here you are
plus
talking
90?
about.
Yes.
No, we'll take it positive only. I'll tell you this. Once let us complete the graph, I'll tell you in the graph. Okay.
Okay.
Now, so now if I plot it again, let us see it carefully once again. Then we'll refer it back. This is my sigma. This is j omega. This is 0, minus infinity. This is minus 7, right? And this is how my branches are starting from, originating from the poles, and I'm taking this point as my centroid, that is 3.5 minus 3.5, and this is the breakaway point as well, right? Now see the angle of asymptotes. One of the angles you have got as, tell me what it is.
Plus
90
90.
degree. Yeah.
Yeah.
So this is your 90 degree, right? And what
Yeah.
is the other angle? 270, right? See, theta 2. So where will be 270? 90 plus 180 plus 270. So this is how you will be having 270, right? Okay. Clear up till here? Everyone,
Yes, ma'am.
centroid and this. So this is how we are drawing the root locus for this given um, gain GSK by S plus 7, right? Now, if I have been given to design a compensator and for which the peak over should be less than equal to 15%, how to proceed, right? Let me tell you that. So, you know that e to the power minus pi zeta by 1 minus zeta square is equal to how much? That is equal to peak overshoot MP, and that is given here as point, that is 15%, right? Or I can take it to be 0.15. Can I find out the value of zeta from here? Please calculate and tell me how much zeta comes out to be. Got it? Yes, Muthu, what is the value? Gaurav?
Calculating, ma'am.
Okay, okay. Do it
Calculate.
fast, please.
0.7576.
Point. No, 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 no. Okay.
Let me
I'm
do it.
telling you. I'm telling you, okay. You
Yes.
just cross check it. What I have calculated, it comes out to be 0.517. Okay. And then you know that cos inverse of zeta, if we take, okay, that is cos inverse of 0.517. You can check, this comes out to be 58.9. Okay, this I've told you in the previous class also, and that problem might be here. Like now we have done, I may have in this here. You can just mm, see here this one. Okay, this root locus for k s s plus 3 s plus 6, and when you have plotted it, you got this, and for the value of zeta which was given, you have found the angle as this. In the same way, we have calculated here the value of this angle for which we have to design the compensator with peak overshoot less than equal to 15%, right? So what we'll do next is that we'll draw a line here, say like this, having an angle of 58.9 degree. Okay. Now see where this zeta equals 0.517 line. This we refer to as zeta equals to 0.517 line is intersecting our root locus. And that point of intersection which is obtained, that is used to find out the dominant roots. You know what are the dominant roots? What do you mean by that?
No, can you once please recite, means recall?
Okay, I'll tell you. It's better you go on asking doubts. I'll tell you everything. Okay. Now see, uh, let us first complete this. Okay. So now if I see points corresponding to this point of intersection, what are its coordinates? Here you can see it is minus 3.5, right? This is minus 3.5, and here it will be, when I've plotted it, it comes out to be J 5.5, right? Correct? Now, once you have obtained the value of this, what does it signify? This signifies dominant roots, and at this value of poles, okay, you have to find out the value of K. Can you do it? What will be the value of K here at DR? Just calculate it quickly and let me know. From here you can find out na K by putting this. This is our step number 2. Okay. Step number 1 is sketch the root locus that we have done. And this step number 2 is the value of K at DR. This DR represents your dominant roots. Okay. Or dominant poles also they are referred to as. How much it is coming out to be? Just put it here, the value. You calculate the magnitude only, okay? Shall I tell you how much I got it?
Is it 3.5 square plus 5.5 square?
How much it is 3.5 square plus 5.5 square? Does it comes out to be 42.25?
Yeah, it's 42 point.
Correct, right? So see, up till here it is clear to you. Now let us go back and clear your doubts, because you'll have more doubts when I proceed. No? So as Muthu asked me one thing, like why we are not using here plus minus 2q plus 1, right? So if we are using, like you can use both positive and negative, because they represent what? They represent the direction of the root locus. See from here. So if we are taking negative, that means with positive angle, they indicate that the branch is moving upwards, right? With the positive angle, they are indicating that the branch is moving upwards. And it is to the, you can see, right of centroid. This is RHS and this is LHS. Okay. So this is to the right of centroid. And if you're taking negative, what does it means?
Clockwise rotation.
Yeah, that means your branch is going downwards. Okay. And the branch is, and this is towards the left of your centroid, right? So you can take both, but and root locus is always symmetrical about the real axis. Okay, and you can take both, but for our analysis we are always considering the positive value, right? There's no problem in taking both. Now as we have taken this dr here, Gaurav was asking, when we talk of the compensation in the control systems, your dominant poles, they have the you can say most significant influence on the transient response of the system. Okay, when we talk of a higher order system, say third order or higher, there are multiple poles, but only few poles, and those poles which are complex conjugate. Okay, not the simple poles. They are basically responsible for the behavior of the system, and these are referred to as your dominant poles. Okay, right? Now if I talk of these dominant poles, they'll be closest to the imaginary axis, and um, if they will be closest to the imaginary axis, the real part will be the largest, right? As the poles will move away from the imaginary axis, the real part will go on reducing, right? Is it correct?
Real part will actually increase as they move away from
No,
the.
no, no, -1 is
Magnitude
greater than
wise,
-2, right?
Okay, okay. I was
Okay,
talking in absolute terms. So
yeah, yeah,
here,
yeah,
yeah,
correct. So, if I talk of this system, if I talk of this system, you can see here that none of the poles are here complex conjugate. We have only two real poles, right? At s equals to 0 and s equals to -7, right?
yeah,
But if a system has one real pole and a pair of complex poles, the complex poles are usually dominant, right? Now you can ask me why, madam, you have brought in this dominant thing, because whenever we are designing and whenever we are designing a system and we are providing the compensation, these dominant roots are very important because they determine the transient response of the system, they determine the settling time, they help in the design, right? So it is mandatory to find out these dominant roots. Clear? Do you get my point?
yeah, ma'am.
Okay. So here we have obtained it at -3.5 plus j 5.5. Right? Okay. Now,
ma'am.
yes, yes, Mutu.
Yeah, oh, I have one
Mm-hmm.
small doubt in the same
Mm-hmm.
handling of
Mm-hmm.
asymptotes.
Your voice is na bit
Oh,
not clear. It is cracking.
yeah. Is it
Mm-hmm.
clear now, ma'am?
Ha, yes.
Yes, ma'am. So there, if we have n minus number of poles minus number of zeros as let's say 3,
Mm.
then if we just take the positive, then there will be some difference, right?
N minus m. That
Here,
means p minus z, right?
yes.
Hmm.
So if we if we keep that as 3,
This
uh,
p
p minus z comes
as
as
3. Huh. Fine.
so then we will have 2q plus 1 by 3 into 180.
Huh. Yes.
So will it still be applicable when, I mean, if we don't consider the negatives?
Obviously, it will always be. We'll see that. We have already done the problems. Based on that, we'll be always following it, no matter what. Okay.
Because if we take minus, then we will get plus and minus 60 degrees.
Mhm.
If we just take plus and move to 1, we will be having 180 degrees, which is plus 180 degrees.
The second part, I haven't got you. Can you please repeat it once again?
Yes, ma'am. If we consider both plus and negative, the
Ah,
angles we get are obtained is plus and minus 60 degrees.
okay.
But if we just proceed with the 0, 1, omitting negatives,
0,
then
1, and for 3 it will be 2 also, right? 0, 1, 2. In that
yes,
case, it
yes.
will. Okay?
Um, okay, the third angle will come as minus 60. That's what you are
Yeah,
suggesting. Okay.
right? Here we have to take into this, na, it won't be always 0, 1. It will be depending upon the value of p minus z, Muthu, right?
Okay.
So you just keep in mind that a positive angle indicates that the root locus
Mm,
will approach infinity moving in a counterclockwise direction. Okay?
yes.
And in negative angle, root locus will approach infinity moving in a clockwise direction, right?
Okay.
Towards the right hand side and left hand side of the centroid respectively, right?
Yes, ma'am.
Clear?
Clear.
Okay. Now this at this value of k, we have to find out the error coefficient of this like system. Okay. So how do we find out the error coefficient? You know that the error coefficient kv of the uncompensated system, that is at the value of k equals 42.5 is 25 is given as limit s tends to 0 s into gs equals, can you tell me the formula?
1 by k.
42.25 divided by 7. Have you seen the videos there how to find out this thing, or shall I tell you how do we reach this?
Please, ma'am.
Okay, now see, if I take a system, a simple system I'm talking of, okay, uh, uncompensated one. Let me explain it here quickly. So I'm taking type 1 system, K, your pi, this is I, S plus Zi, and here I'm having S, J, S plus Pj. Okay, zeros and poles, and this is type 1 system, so here we have s in the denominator. So if I want to calculate the error coefficient of this uncompensated system, can I write it like this? Kv, this is velocity or error constant, of course, is equal to limit s tends to 0 s gs equals to k. I can write it like as, right? Okay, ss gets cancelled, I'm left with this.
Yeah.
Okay. Right. Now, you know that when we are designing a cascade lag compensator, I'm talking about a cascade lag compensator, then if you remember, the transfer function of it is given as s plus 1 by tau when we are talking of zeros, and s plus 1 by beta tau where beta is greater than 1, right? So basically, I'm adding a what here? A 0 and a pole, right?
Yeah.
Clear up till here?
Yes, ma'am.
Okay. Now, for the lag compensated system, the error coefficient will be what? KVC. Okay. Because we are talking of now this compensated system, it will be limit s tending towards 0 s g lag of s into g of s, right? That is what we do. we add a compensator in cascade with the existing system, right? So that's why we are getting this G lag of S into GS, right?
Yeah.
Is it clear, everyone?
So when we are calculating velocity
Mm-hmm.
error constant, we are assuming a step input.
Right.
Okay.
Okay. Clear?
Yes. Yes, ma'am.
So now, can I write down this as beta into K? I'll get it like this. If you solve this, you will get that the velocity error constant for the compensated system comes out to be this. Okay.
Got it, ma'am. Yeah, got
Yeah.
it.
So can I replace this entire thing by this? Right. So this will be beta multiplied by the KV for uncompensated system. Right. So from here we have deduced this expression which we are going to use where in our problem. Okay. So you can say that error coefficient increases by the factor of beta, right? And from where this beta has come into picture? This beta is obtained by connecting a lag compensator in cascade, which is going to have a transfer function of this form. That is S plus 1 by tau, S plus 1 by beta tau, right? Okay.
Yes, ma'am.
So next, let us see what will get this value as. So if we calculate this, this is our value of K, right? Okay. And here we'll get this as 6.036. Clear?
Yes, ma'am.
Okay. And what will be the steady state error? We can calculate it from here.
That will be inverse of this.
Yeah, right, right, right. And steady state error, that will come out to be uh, for this uncompensated system as 1 by kV, that is equal to 0.1657. If you solve it now, you'll get this much. Okay. Now, what is step 3? Step 3 is, you just remember these steps which we are doing one by one. Okay, it will be easier this way. So step 3 is, we have to take the value of beta as 20. You can see here that in the problem, the design considerations were that you have to improve the steady state error for unit ramp input. Okay, that's why we have taken the velocity constant error, right? To improve by factor of 20. So here our beta is now 20. Okay. Now step 4 is, you have to choose the compensator pole zero pair so that the compensated value of the error coefficient is 20 times the error of the uncompensated system. So for the uncompensated system, we have calculated to be 6.036, right? So 20 into point, how much it was? 6.036. 6.036. That comes out to be 120.7. Right? Clear up till here?
Yeah.
Right? So now, next, what we'll do? We have to make this. We have to design this, right? So I will choose a compensator 0. I'll choose a compensator 0. Listen it carefully. At s equals minus zero point 0.2. Okay. That means 1 by tau is equal to minus zero point 0.2. This is my 0, right? Clear? So what is the value of tau? Minus 1 by zero point 0.2, right?
Yeah.
Now see, you can ask me, ma'am, how you have reached this conclusion that s is equal to minus zero point 0.2, right?
Yeah.
Okay. So I've told you, and it is observed that the when we are designing the compensator, the poles and zero should be near to this imaginary axis and near to this origin. Okay. So we have taken a value of s equals minus zero point 0.2, right? Clear? Less than 1, less than minus 1 to be precise. Now, if we
Again,
take
is
this,
this arbitrary or
yeah,
how?
we have
Oh,
taken it arbitrarily, right?
okay.
Okay. Now, if I have taken this tau is equal to minus 1 by zero point 0.2, you tell me where will be the pole? Where will be the pole which will get here? So, pole is your,
-5.
yeah, correct. Minus 5, not minus 5. This is, see here, pole will be at
Okay.
minus
Beta
1 by
time.
beta tau, right?
Yeah.
Right?
Yeah.
So, minus 1 by tau, or that I can write to be zero point 0.2, and the value of beta is given as 20. So how much it will come out to be? 0.01 with a obviously negative sign. Yes? Is it
Okay.
clear?
Yeah.
Since this is 0, and I'm telling once again, the pole can be written as minus 1 by beta tau, and tau is how much? Minus 5. Okay, minus 1 by, this is 20 into 5, right?
Yeah.
Minus 5.
Minus, this will be plus 5, no? Minus zero point 0.2. Okay.
Yes.
So this is how much? This is come out to be minus zero point 0.01, right? So I've got my transfer function for the lag compensator as s minus of minus zero point 0.2, that is s plus zero point 0.2 divided by s plus 0.01. Correct?
Okay.
Okay?
Ma'am,
Yes.
so 1 by tau is negative and tau is positive.
1 by tau is, this is minus 1 by tau, no?
Okay.
To be correct. Correct?
Okay.
S plus 1 by tau, right? Correct?
Yes.
So, can I write down now G lag S and GS equals K? The value of K we have calculated as how much? 42.25. Okay. Then S plus zero point 0.2, which we have obtained here, divided by S, S plus zero point 0.01, S plus 7. Correct?
Yeah.
Correct? So
Yes.
now can you find out the error coefficient for this compensated system from here? I'll tell you why I'm asking this. What will be the error coefficient here?
We
Calculate it,
already
please.
didn't we already calculated it
That
when
was
we,
for the uncompensated system. Now
but
we
if
have
we,
compensated. Yeah.
so divide means that will be beta times uncompensated.
No, no. This is, see, this is limit s tends towards 0. S G lag of S G of S. Earlier, see, we haven't found this with the compensation, and here now we are recalculating it with the compensation, like cascade compensation, right?
Okay. Okay.
Got it, Gaurav?
Okay.
So SS gets cancelled, and how much it comes out to be? 42.25 into zero point 0.2 divided by 0.01 into 7, and see how much you'll get. When you'll calculate it, you will get it 120.7. Okay. Now you can see that
Which
how
is
many.
same as
Yeah.
beta times uncompensated error coefficient, right?
Yeah. That is, you can see there is 20-fold improvement.
Yeah. Yeah.
Okay. And here the location of dominant root dr is preserved. You can see here. Okay. Right.
Yeah.
So can you find out here the angle that is contributed by this compensator, which we have connected in cascade?
That will be
Hmm?
0.
No, no. I'll tell you how to find out that
Okay.
thing. Okay. You can do this G angle of G lag at S equals dr equals, what is the value? Minus 3.5 minus 3.5 plus J 5.5, right? Minus 3.5 plus J 5.5, and tan inverse of minus 5.5 by 3.5. You find out uh, how much it comes out to be
This is the angle from the origin, right?
from the.
Origin.
This is the angle that will be contributed by this. You calculate it. I'll
By
tell you.
by by what? By the pole at origin, right?
This, no, this is not the pole at the origin. This is
Okay.
the, yeah. How much you're getting?
Minus
1
1.004.
minus 1.00, which is negligibly small, very, very small. Okay.
This is in
It is
radians.
this this angle. Okay. This one, Gaurav. Here we are having this now.
Yeah.
Okay. So this is the angle contributed by this pole, right? Which is very
Which
negligible. Yes, Muthu, you were saying something?
This angle is in radians, right, ma'am?
Degrees.
This minus 1 point.
Yeah. 1.00. So it doesn't affects like my improvement by adding the compensator, right? So can you solve now problem based on this, all of you, by following these steps? Shall I summarize once again the
Yeah.
steps?
Yes, ma'am. Yes, please.
Okay. So the
Ma'am,
first thing is, yes, Muthu,
this angle is from the negative x-axis to the this ring.
negative.
X-axis to the here. Ah,
This one,
yeah. This angle we found now. Is it
Angle
from?
of 1 degree.
this 1 degree, na? Yeah, this is, so see, this is just the angle that we have obtained by adding the like transfer function for this, what, our,
Compensator.
yeah, compensator, right? And for that compensator we have found out the dominant roots or dominant poles. So this was the angle of the dominant poles that we have obtained here. So where, how do you draw that? Just let me show you this once, it will be clear. See, if I have a imaginary pole like this, okay, can you see this?
Mhm.
Yes, ma'am.
It's a
So
imaginary
see,
poem.
yeah, can
Uh,
you see this?
so I mean,
This
complex
is
pool
a
thing.
complex, sorry, imaginary,
Ah,
this minus 2 plus
plus
2j,
2K.
then minus 2 minus
Yeah,
2j.
2K.
So how do you draw the angle here like this? It won't be from the origin, right?
Okay, okay. So this
Got
angle
it?
of departure.
Right.
Okay,
Okay.
okay, ma'am. Yes,
Clear?
yes, ma'am.
Okay. So I'm just summarizing it once. Listen carefully. So if I want to design a lag compensator for improving the response, then I have to first sketch the root locus for the uncompensated system, right? Calculate the value of zeta, right? And then one thing I forgot to tell here, that you have to find the value of omega n also here. We have calculated the value of k, but we haven't calculated the value of omega n. Okay, I'll tell you it in the next problem. Okay. So for dominant poles, we have to calculate the value of k, right? Then we have to find out the corresponding error coefficient. Then we
Ma'am,
have to
one question. So we
Mhm.
are given this peak overshoot value, like
Yeah, we have
15%,
been
right?
given. We have been
So
given.
yeah, so from that
Mm.
peak overshoot value, we have to find out the value of zeta,
Right.
right?
Right.
And then we will find out the value of omega n.
And theta. Theta.
Where is theta?
Theta we have drawn cos inverse of zeta is equal to theta.
Okay, yeah, okay.
Right?
Um, yeah.
Okay.
Mm-hmm.
Then we have what we have done. We have calculated the gain k at the dominant root.
Yeah.
Right?
Can you repeat this step?
Which one?
Value of k at dominant root.
Yeah. Value of k at dominant root. How we have calculated this?
Yeah.
Okay. So see, we have calculated theta from
Yeah.
cos inverse of zeta. Then we have whatever angle we have obtained, we have drawn it from origin, and we have seen that where it in cuts our root locus, which we have drawn for the uncompensated system, and corresponding to that point of intersection, we have calculated, or we have seen the value of the pole that we have obtained as minus 3.5 plus j 5.5, right?
Okay. Yeah.
And then
Got
we
it.
have substituted, and then we have calculated this,
So
right?
this value of pole, the S
Mm-hmm.
value, is to be substituted in our GS function
Yes, right? Like,
or characteristic equation to find out the value of k.
yeah. As you can see here also, this is how we find out the value of k. I've told it in the previous class, Gaurav, how to get it, where it cuts that way. Okay.
Okay. Thank you, ma'am.
Last time we have done this problem, the very first problem for root locus, because I knew that we'll be using it in the design. That is minus 1.2 and J 1.6. You can go to the previous lecture, okay, and check how to
Yeah.
find out the value of k, right?
Thank you, ma'am.
Done?
Yeah.
So now we have to determine the factor by which the error coefficient is required to be increased. And here it was given as beta equals to 20, right? So we
Yeah.
have to next locate the compensator 0 very close to the origin, and then the compensator pole at s equals minus 1 by beta tau, right? With beta that has been already given in the previous step, right?
Yeah.
Clear?
Yeah.
So this is how we design it.
So
So,
this
huh,
value that we have taken 0.02,
hmm,
sorry, 0.2.
0.2, that is arbitrary, right? And you can mark it here like a compensator pole at S equals, you can mark it like this, compensator pole at S equals minus 0.01, and then compensator,
Zero.
yeah, compensator 0 we have taken, no?
Yeah. Zero is
Yeah.
0.2.
Yes, yes. And 0 is, no, we are doing something wrong.
No, pole
Yeah,
is
we,
correct, ma'am. 0.01.
this is compensator 0 at S equals minus zero point 0.2, correct. So we have to mark again a 0, that is, this is say, okay, somewhere here, okay.
Yeah.
This is 0. Compensator 0 at S equals minus zero point 0.2, right?
Okay.
So this completes our root locus showing lag compensator with all the steps which we have used for its design, right?
Yeah.
Is it clear to everyone? Shall we go to the next question?
Ma'am,
Yes.
the angle we found at the last, I think it's
That
radian.
is that is not required. This one, this you're
Okay.
telling, this I have just told you for additional information. Just
Okay.
leave it. Okay.
Okay.
This is not at all required. Okay.
Yeah, sure. Okay.
Okay. So next, let us see the cascade compensator design for, I want to do a problem based on,
Excuse me, ma'am.
yes.
Um, where will I get all the old recorded live sessions?
Can you please repeat once again? I could not hear you.
Where will I get all the old recorded live sessions, ma'am?
In control engineering channel.
Control engineering channel.
Right.
Can you show me?
Yes. You can just go on the website and you can see, or otherwise I'll share with you that uh, Google sheet. Okay. There also you can see.
Okay. Then for analog and DSP,
That you have to ask in the respective sessions, right? Shall,
thanks.
okay.
Can you please send it to me?
Okay. Let's do one more problem. Okay. Now let us design a lag compensator for a unity feedback system where GS is equal to K by S plus 1, S plus 3, S plus 5, right? And it has to yield the specifications of peak overshoot less than equals to 10% and step error coefficient greater than equal to 4, right? Okay. So now we have to follow the steps which we have discussed right now. So first of all, what you have to do, you have to draw the root locus for the uncompensated system, right? Can you do it fast? If we see step 1, root locus. So number of poles 3, that is s equals -1, -3, -5. Number of zeros are 0. So next, let us locate it on the S plane. Here we have a pole at -1, -3, and -5. Have you tried this thing with MATLAB?
No, ma'am.
Okay, I'll send you the code. Don't worry. -5, right? And one of our points will be minus infinity, right? Now I have to see that where the root locus branches will lie, right? So if I see from here 0, so no root locus branch from -1 to plus infinity. Come to -3, 1. So definitely here I'll have a root locus branch between -3 and -1. Come to -5, again 2 poles, even number. So no root locus branches will lie between -5 and -3. Come to minus infinity, right? So again, a root locus branch will lie odd number. If you stand at minus infinity and see towards this, -5, -3, -1. 3 poles, odd number. So definitely there will be a root locus branch between -5 and minus infinity. Clear this one? So what are the directions? Originate from pole. So towards this side, towards this side, opposite to each other. So when we have this uh, thing, like two branches are coming towards each other, then we have what? We have a breakaway point, right? Clear? And from -5, we have again a branch that is going towards minus infinity. Clear up till here?
Ma'am,
Yes.
the breakaway points,
Hmm.
when will it not be the midpoint?
When it will not be the midpoint.
Midpoint.
What is that midpoint thing, Muthu?
I mean, because so far, okay,
Huh?
here most probably the breakaway point will be -2, right?
Minus?
2.
-2. No,
No.
no. We'll see. We'll
No.
see.
Okay.
Whenever we have this condition where the two branches of the root locus are approaching towards each other, we have a breakaway point. Whereas in case of zeros, we have a break-in point. Okay. We have done a problem in the previous class. You can just go through that. Okay. And
Yes.
we'll see what will be our centroid here. Right. So we have drawn this. The second step is what? You have to find out the centroid. Right. So what will be the centroid here?
-3.
Minus, have you calculated?
3,
It is coming out to be 3.
-3, or
-1, -3, -5, -0 by
Are we finding centroid or breakaway?
centroid. Where
Centroid,
first?
yeah. Okay.
Okay.
Centroid is -3.
Divided by
3.
3. So -9 by 3, that comes out to be -3. Okay. Now next what we have to find out? Angle of asymptotes, right?
Yeah.
So angle of asymptotes, that is theta equals to 2q plus 1, 180 degree divided by p minus z. So here, what will be Q? Q will be 0, 1, 2. Right, Muthu? P minus Z minus 1. That is 3 minus 0 minus 1. We'll have 3 values, right?
Yes, ma'am.
Correct? So the value of theta will be equal to 60 degree, right? 180 degree and
300.
300 degrees. Okay?
Yes. That 300 is the minus 60 degree.
300 is the
Minus 60.
yeah, you can say that, but don't go after minus
Okay.
sign.
Yeah,
Okay?
yes. Yes.
Okay?
Yes.
So what is the next step? Once
Breakaway
you've kept
point.
breakaway point, correct. Find out that is dk by ds is equal to 0. Okay? So how much it will come out to be? Can you calculate it quickly?
Minus 1.8452.
Correct. Absolutely correct. Minus the breakaway point will come out to be
Minus 1.8452.
minus 1.8452. Okay. Can I write down this as minus 1.85, rounding it off? Now see, where is the centroid here?
Minus
Minus 3.
Minus 3. And where is the breakaway point?
minus 1.8.
Are they coinciding?
No.
No.
No. Right? So if I plot it, this is 60 degree, 180 degree, and 300 degree. Right? Okay. So how I'll be plotting it 60, then 180 and 300. From where I have to
Um,
plot that? From the centroid, right? And centroid it is at minus 3. So listen carefully, huh? Muthu, it will be clear to you now. So minus 60 will be coming somewhere here, like this, right? 60 degree, then 180 degree, right? And 300 will be,
Downs.
yeah, here, right?
Yes.
Okay. And my root locus is breaking away from a point of minus 1.85, means somewhere between minus 1 and minus 2, right? Near to
Yes.
this.
Yeah.
Okay.
Yes.
So the root locus will be like in the same direction as this, branching away in the direction of 60 degree, right? In the direction of 300 degrees. Okay. Like this, right? And 180 degree. 180 degree for this.
Minus.
Clear? Is it clear now? What is the purpose of this centroid and what is this angle of asymptote telling us? So this will be going towards infinity, right?
Ma'am,
Hmm.
what will be the angle at which the root locus will leave the real axis?
60 degree. This is
No, no, no.
60 degree.
Not at the centroid, but
No,
they'll
no,
actually.
no. This root locus will be like you have to draw at an angle of 60 degree only. That is what it is showing. What is this angle of asymptote? It shows that
That infinite, when it approaches
It says
infinity, it
infinity.
will, yeah, it will reach 60 degree. What I'm
Yeah.
talking about is at breakaway point when the root locus will bifurcate from real axis.
No, no, you're just mixing these 2 points. Like when we have drawn this at 60 degree, like we cannot draw anywhere. Like we cannot draw it here. We cannot draw it like
So
parallel.
I got that, ma'am.
Hmm.
The 60 degree
It is
asymptote
approaching.
is for infinity values. How the root
uh,
locus will,
Angle of departure.
Huh. It is showing that how at what angle from the breakaway point this is leaving towards infinity. Okay. This breakaway point is leaving at what angle? That is your question, right?
at breakaway point, they will, means root locus will leave the real axis.
Right.
So now, at what angle will it leave that?
Breakaway point. From breakaway point, the root locus.
Yes,
That will be always at 60 degree, right? Because see, 180 degrees for this, 60 degrees for this, and 300 degrees for this, right? Going towards
60
this.
degree is the asymptote angle. So at
Asymptote angle is for this only. For root locus only, we are finding out the angle of asymptote. Okay.
yeah, so when k approaches infinity,
Mm-hmm.
this is the asymptote line which root locus will follow.
Asymptote line, yeah. Asymptote line parallel to that asymptotic angle, it will be.
Yeah, I got that point. But
Mm-hmm.
now we are at this breakaway point, that is between, means just before -2.
Mm-hmm.
Okay, so if I go by what you are saying, or if I'm getting it right, what you are
Mm-hmm.
saying is at that particular point -1.8. Okay, at that point it will directly go at an angle of minus 60 degree from there, and 300 degree, sorry, 60 degree and 300 degree. Is that what you are saying?
I mean to say that the yeah, someone.
Two has got something to say.
Yes.
Uh, yeah. Yes, ma'am. I think Gaurav sir is asking.
Mm-hmm.
So from the minus 1.85 point, two curves are leaving, right?
Right.
That curve can be drawn in a very various variations. So the angle it
The
leaves in that minus 1.85, it is not 60 here, right?
I agree what he wants to say, but when we have got this line from the centroid showing the angle of asymptote, the root locus which I'm drawing from the breakaway point, it should be parallel to the 60-degree line, right?
Yes, ma'am.
But
You
that
cannot.
will only happen when k
Okay,
approaches infinity.
right. And you are asking me, you want to know this angle, right?
Yes,
Kind of. I
at
could
Yes.
that
have
breakaway
drawn
point.
straightly also, right? With the
Uh-huh.
60 degree. But it is having some curve and then bending to
Yeah.
make
What
it
is that? We have to, this originates and it has to be parallel to this asymptote, right?
uh,
So
yeah.
eventually it will get to that asymptote. Yeah. So
Right, right.
that is clear. So it will make an angle of 60 degree with centroid. But at this breakaway point,
So the angle of departure is this what we call as angle of
No,
departure?
angle of departure always exists for your complex poles, and angle of arrival exists for your complex zeros.
Yes.
Here
Okay.
we don't have that. Okay,
Okay.
I got your point, but
okay,
I'll let me we'll discuss it later on. Okay, let me see to it.
okay, fine.
Okay.
Yeah. So
I think there is one more formula where the root locus cuts the imaginary axis.
Where the root locus cuts the
Imaginary.
imaginary axis
Uh,
is what.
maybe
Mm-hmm.
if we go through that, maybe that poses some restrictions on drawing this.
Okay.
No, not actually. That is just to find out where it is stable and unstable.
Okay.
Okay. So
But I think we are digressing. We should continue
yeah,
with these steps here.
yeah. Well, I'll see to it. Whatever you are asking, let me check it. Then I'll get back to you for that. Okay.
Yeah, yeah. Thank you, ma'am. Yeah.
Now, where were we? We have seen that this is going to be our root locus. How, and this is going to cut this imaginary axis at these 2 points, है ना? Parallel to 60-degree. Then here parallel to again 300 in the same direction, 300 degrees, right?
Okay.
And when I see this point and I plot it on the paper or with the help of MATLAB, I get this as plus j 4.8 and minus j 4.8, right? Okay. So my root locus is complete now. Now I have been given here that peak over should be less than equals to 10%, right?
Yeah.
So can I find out my zeta from here? Next, now I have like done my root locus. I'll again start with the procedure that is required for my designing the lag compensator, right? So uh, e to the power minus pi zeta by 1 minus zeta square, that is, that will come out to be zero point 0.1, right? Or zeta will come out to be how much? If you solve this, you'll get it as 0.59. Similarly, cos inverse of zeta is equal to theta, as we have done in the previous question, and I get this as 53.8. Okay. So now you have to draw a line that will be coming out radially outwards from this origin. Okay. And it makes a angle of 53.8 with the negative real axis. Okay. So it will be something it has become. Let me use a different color. So if this is you do a subtract this from 180, how much you'll get? 53.8. You'll get something as
7 point.
126.2, right?
Yeah.
So this angle is, you can say 126.2, or this angle is what we have calculated, right? And the point where it cuts the root locus, that will give us the value of dominant roots dr, right? And then when I mark the points on the real and imaginary axis, I get the value of s as minus 1.4 plus j 1.9. Okay, this thing. Okay, so the point of intersection of this line with root locus of the uncompensated system is identified,
I
right?
have one question here, ma'am.
Yeah, yeah,
So
please.
the peak overshoot formula that we have,
Mm-hmm.
NP is equal to E to the power
Mm-hmm.
minus pi zeta. This
Mm-hmm.
formula we derived it for the second order system, second order equations,
Yeah,
transfer
yeah.
function. But the given function that we have is a higher order.
We'll be using it for this also. No problem. We can use it here also. Okay.
Okay, that sounds like okay. I mean, I'll
And also,
take it by on your word, but is there any justification for using the same formula for higher order systems?
We have second order system we have taken, but like in general, we can use this formula for calculating the overshoot. Okay.
For any order?
Yes. Any order means generally we are dealing with right second order or third order systems,
Okay,
right?
yeah, fine. So similar way, we can also find out omega n,
Right. Similar way.
even though the formula is actually for the. But what will be omega n? We don't have omega n formula.
We what we do,
How will
Gaurav,
we?
generally, like we typically like approximate our third order system as a second order system only, and then we calculate it using this. Okay, we do the approximation. Like there are various methods of approximation, and we consider our higher order systems and approximate them to be our second order systems and use this expression, right? Let's
And
not again.
do we check that approximation? How good that approximation
No,
is?
no, we won't go into details of that.
Okay, fine.
Okay.
So we left out the part of finding omega n in our last problem.
Yeah, we'll do it right now. We'll do it.
Okay,
Okay.
okay.
So this this is okay. Now the dominant root. The next step says we have to find out the dominant root, right?
Yeah,
So that has to be calculated at s equals minus 1.4 plus how much it was?
J
J
1.9.
1.9, right? And what was the gain? That you have to calculate, right?
Yeah, by substituting this value of s.
Value. Correct, correct. And K will come out to be, you please check it, huh? When you will just revise. So here in the problem, it is given as the step error coefficient, right? So Kp for the uncompensated system, that is given as limit s tends to 0, g of s.
Ma'am, sorry for
Haha.
interrupting you. Can
Yes.
we go through this step? Means s is equal to minus 1.4 plus j 1.9. How did we arrive at this value for
This
s?
this I told you, no?
Yeah,
We have to like see at what point my theta line, which I'm drawing from the origin,
yeah.
is intersecting the root locus, right? And corresponding to that value, if I see it, my S comes out to be minus 1.4 plus J 1.9. Okay.
Yeah, so this
And
exactly this point, this step, how am I arriving at this? Means I know cos theta is equal, or means I know
mhm,
the value of theta.
you have to plot and see. You have to roughly plot and see. Okay. That's why I've plotted here on the graph paper to show you guys. See how we are arriving this. See the very first question. Here I'm plotting theta, right?
Yeah.
Drawing a line from O to A, and this
Okay.
OA is cutting my root locus at C, where minus 1.2 J 1.6, right?
But are we just having a look at the graph and then?
Yeah, yeah, definitely.
But is there isn't any formula that will give me exact?
No, you can use a MATLAB code, which I'll provide, and then you can just verify this process which we are doing analytically with that. Okay, MATLAB code.
So um, I'll use this value of s to determine the value of k as well,
K.
right?
K.
K.
Right.
Yeah.
At that
K.
value of S, what is the value of K? Right?
Okay.
Got it? So if I put the limit S equals to 0 in my transfer function, you can see here it is 1 into 3 into 5, 15, right?
Yeah.
And this is 19.5 divided by 15. So I get the step error coefficient as 1.3. So this is a step error coefficient. It is asked in the problem, right? You can see, right?
Yeah.
And then the next step is improvement factor. What is the improvement factor?
That
Step
is
error
beta.
coefficient should be greater than equal to 4, right?
Yeah.
So the step error coefficient improvement factor, that is Kp, that is specified to be 4 divided by Kp for uncompensated system. So this comes out to be 4 by 1.3, and that is 3.08, right? So now see here again, the value of beta is not given, right? So
Yep.
let us choose the value of beta as 5. It should be like greater than 1. You can choose it to be 10. You can choose it to be 15. Let us choose here 5. Okay. Let us choose beta equals to 5. Again, for the lag compensator, as we have taken in the previous problem, 0, that is close to origin, at s equals minus zero point 0.2. Okay, right?
Yeah.
So where will be my compensator pole? Tell me.
That will be
Hmm.
beta divided by beta.
Yeah, correct. Minus zero point 0.2 divided by beta. That is how much I've taken this as 5. So it will be minus zero point 0.04. Right? Okay. So what will be my transfer function for the compensator? S plus zero point 0.2 divided by S plus zero point 0.04. Right? And then the lag compensated forward transfer function will be, that is equal to S plus zero point 0.04, S plus 1, S plus 3, S plus 5. Right? And what will be the step error coefficient? Here,
Uncompensated error divided by 5.
how much it will come out to be?
What was the uncompensated error?
Or you can find it like this also.
Yeah. So,
KPC limit S tends to 0, right?
yeah.
And this will be G lag of uh, for G of S for this lag compensator, and G of S for this, and it will come out to be C 19.5 into zero point 0.2 divided by 0.04 into 1 into 15. How much it comes out to be? Check.
6.5.
Correct. Is this clear what we have done today? Can you do it on your own now?
Some things are means using graph and finding out the value of s
Hmm.
from the graph. So if we are doing it manually, that will be not uh,
That is
means-
very easy. You have to just follow the steps and you have to just use a graph paper, plot the values there quickly, and you will get the answer.
but
It is
if I
very
get
easy.
this question, if I
Mm-hmm.
get this question in my quiz,
Mm-hmm. It will hardly take 5 minutes when you practice, na? It will hardly take 5 minutes to do, not more than that.
and then the value of beta, that is also taken, like we took it to be 5 in this case.
Doesn't matters. Like if it is not given, you can assume it to be 5, 10, 20. But if it is given, you can take, as in the previous problem, it was given 20, right?
Yeah, yeah, okay, okay, fine, yeah,
Uh,
fine.
shall we do more problem here? One more problem? Or shall you? Shall I like?
Ma'am,
Yes.
the peak formula we are using, it is when the input is step, right?
Input is step.
Step. Ah,
Mm-hmm.
so here the input can be anything or
Where,
mostly.
Muthu? Once again, please repeat.
Um, no, the formula we are using as a peak value
Mm-hmm.
formula.
Mm-hmm.
It is when the input is step.
The peak overshoot you're telling?
Yes,
Yes. See, we can use it for like uh
the inputs also.
ah
Because in one of the sessions when professor was there,
mm-hmm.
when I asked him, he told for other inputs we may have to modify the formula.
Generally we take step only, step input only. As Gaurav has asked me a similar like doubt, now if we go for higher order systems, are these expressions valid or not? So we do the approximation. Okay, so
Mm,
step is the simplest of the signals which are used for most of our analysis, right?
correct.
Okay, so in we just do the generalization that we assume okay it is a step input. Okay.
Now can we
Okay.
go back to finding the value of omega n for this?
Yeah, we'll go. I'm looking for a problem where you can just have a lead compensator design and there we'll see. Okay. So let us complete one of the problems based on this.
What we did is lag compensator design.
Right, right. So that you have an idea of like all the types. That is what I lead compensator. Let us do this one of the problems. And omega n is not a big thing to calculate, right? I'll tell you how to calculate it uh, right now. I'll tell you after doing this. Okay. Okay. You just note down this problem. Let gs is equal to k by ss plus 2, for which a lead compensator is to be designed. Okay. To meet the design specifications of peak overshoot less than equals to 16% and settling time less than equals to 2 seconds. Okay. Now see here, till now we have taken the error coefficients. Here you can see settling time has come into picture. Okay. So let us now again do the entire process and see how to design a lead compensator for this system, right? So can we quickly plot the pole zero plot here and the root locus? This is your sigma j omega, right? I have a pole at origin and I have a pole at -2, correct? And if I see from here, from 0 towards right hand plane, no roots, so no root locus here. And when I see from -2, one pole at origin, that is a odd number. So my root locus is going to lie between 0 and 2. Okay. So it will be like this, originating from both the poles. And of course, if I look at minus infinity, again, two poles, even numbers. So my root locus is going to lie between 0 and -2. Okay. I'm like taking a scale bit bigger because there will be too many like taking -1 here and I'm taking -2 here, right? Okay. I'm not writing all the steps. Is it okay with you guys?
Yes, ma'am.
Okay. So centroid, where it is going to lie? Can you tell me quickly? That is s equals to 0, s is equal to -2. So -2 and no zeros. So summation of poles, that is -2 -0 divided by 2. That will come out to be at -1. Okay. So centroid is for root locus. The centroid comes out to be -1. Okay. And what are the asymptotic angles? Theta. Here we have two poles. So your Q will be 0 and 1. Okay. 0, 1 up till P minus Z minus 1. So here P minus Z is 2, 2 minus 1, 1. So here I'll have theta as, can you tell me the values?
90 degree and 270 degree.
Correct. 90 degree and 270 degree. Right? So what will be the breakaway point? Can you find out quickly? dk by ds is equal to 0, for which you need to calculate 1 plus gs hs. How much it will come out to be? S plus 2 plus k equals to 0. So k is equal to minus s plus 2, or dk by ds is equal to how much? Minus 2s.
-1.
Again -1. So s comes out to be -1. Okay. Right. So breakaway point is also going to lie at -1, centroid also at -1, right?
Ma'am,
So, yes,
-2 is -2, right?
correct, -2, right? Is
Yes.
it correct?
Yes.
It is going to lie here. I've done by mistake when I've rubbed it. It is here, right? Okay, right? So, -1, if I draw the angle of asymptote 90 degree, the breakaway point is also here, and this is 270 degree. So this is how my root locus will appear. Correct? Okay.
Yes.
So now, what is the next step?
Zeta.
Correct. We have to find out again the value of zeta, and zeta can be obtained as our peak overshoot is given as 16% or 0.16. If you calculate the value of zeta, it will come out to be 0.5. And now if I want to find out this zeta, what this zeta equals to zero point 0.5 line is making an angle that will come out to be cos inverse of 0.5 as 60 degree with the negative real axis, right? So can I draw it here? Like this. So this is zeta is equal to 0.5 line, and it is making an angle of 60 degree with the negative real axis, and it is cutting my root locus at what point? Minus,
-1 plus J 1.732.
oh, great. How we have calculated?
Tangent 60.
Correct. Right. Here we can do it. Okay. So this is our value of S. So what will be K here? K can be calculated quickly from here. Okay. K comes out to be 4 here. For this, K comes out to be 4. So the roots which are here, our dominant roots we can say, or dominant poles at S equals -1 plus J 1.732, for K equals to 4, they will give us a peak overshoot of 16 degree. Sorry, 16%. But settling time is how much it is? Can you calculate that? The settling time should be less than equals to 2 seconds. Can you calculate the settling time here, please?
We will need the value for omega and there, right?
Yeah. 4 by zeta omega n.
Yeah. So we have the value of zeta.
Mm-hmm. See, settling time is 4 seconds. It is given, right?
Less than 2 seconds.
Huh. Here we are getting a settling time of 4 seconds, right?
How did you find that?
That is, you have to calculate it.
So we have found out the value of k. K is equal to 4.
Mm-hmm. You see, you can see, um, you have calculated the angle associated with damping ratio of 0.5, right? That
Yeah.
is, that comes out to be 60.
Yeah.
Now, I guess you have, you know this expression, like if I write down this omega d as 2 into tan of 60 degree, okay, how much it will come out to be, please see.
2
Tan
root
60
3,
is root 3, right?
3.4. Yeah.
3.46 approximately, right?
Yeah. Yeah.
So can you calculate now omega n from here? From the angle of this damping ratio line, which is zero point 0.5 here, you can calculate this omega d as 2 into tan of that angle. Okay. Now can you calculate omega and see how much you're getting, please?
Why did we use omega d equal to 2 tan 60?
This is how we calculate it when we have this line. Okay. This for the damping ratio 0.5.
So on this triangle, which side is omega n or omega d? What to say? Is there means can I show omega n here somewhere on this
Yeah, I'll
graph?
tell you first, you calculate the value.
Okay, sure. Yeah.
How much you're getting?
Three point nine nine five two six.
Correct. 3 point omega n comes out to be 3.99. That I can take approximately equal to be 4 second. Yes.
Yeah.
Okay. So let me finish it quickly. Then we can discuss it further in the next class as being proposed by you guys. Here we are getting a damping rate, a peak overshoot of less than 16%, but settling time is 4 seconds. But here the condition for designing the lead compensator is that our settling time should be less than equals to 2 seconds. Okay. Now it is not possible to change the settling time with gain adjustment while we are keeping this peak overshoot as 16%. Okay. So if both the specifications are to be satisfied, right? Okay.
Yeah.
So that means my dominant roots, they have to be located at located at like some other place. I cannot take this as my dominant roots, right?
Okay.
Right? Which you have found here as this minus 1 plus j 1.732, right?
Okay.
Okay. So where will be the dominant roots now lie? That is a question.
Yeah.
Got my point or not? Everyone, please tell me. Then I'll proceed further.
Yeah. Got your question. Yeah.
Got it? So now there is a approach to how to find out the real part and the imaginary part of the dominant roots. Okay, listen it carefully. So, what do I do? The real part of dr, that is obtained from the specified settling time, and the specified settling time is given as 2, right? So what I'll do, I'll take the time which I'm getting here. Okay, sorry, which I have this is 4 second, no? This is 4 second, no? The settling time,
That is what we are getting from the
omega
existing.
n. Yeah,
Yeah.
yeah. So this is settling time. By mistake, I have written this. So by 4, by real part, and what we want to get as specified, that is 2, right?
Yeah.
So what we'll do, the real part will come out to be, real part will come out to be 2. Okay, and the imaginary part of dr, here I mark it as asterisk, right? That is based on the angle of the damping ratio line which you have just calculated. Okay, so it is given as, what we have taken as 2 tan 60 degree. Okay, that comes out to be 3.46. This is how you will calculate the imaginary part. Okay, so once again, I'm repeating. And if you want the expression behind the calculation of this, we can discuss it in the next class. That is, if we are given the specification for the settling time and we are not meeting it by getting the dominant roots as obtained from the root locus, then we have to use this formulae for the real part of dr we can calculate by this, and imaginary part of dr we can calculate by this. Okay, do you get a little bit?
Not sure how did we arrive at the value of 2 for real part of dominant root.
See, what is the value of specified settling time? 2.
Yeah.
What we have obtained, that we have
4.
obtained as 4.
Yeah.
So what we do, the specified, this is the specified value, right?
Yeah.
And this is the value obtained
Yeah.
by dr, right? We have calculated it from there only. Okay, so this gives real part as 4 by 2 equals to 2,
So if
right?
specified value is 1 second, then
That will be 1 by real part equals to 2. No, that will be 4 by real part equals to 1. And then we can calculate the real part of s. We have to calculate now s, no?
yeah, yeah,
That is,
got it. Yeah.
okay?
Yeah.
That is s for the dominant poles we have to calculate, right? Because it is meeting our one requirement but not the other one.
And the imaginary part is whatever
Give,
real part we have got, that multiplied by tangent 60.
right.
Okay.
Okay. Here there is one more step. You see here. If I see now where s equals minus 2 plus minus j 3.46 is going to lie. It is going to lie somewhere here, right?
It will again
This
be on
was
that cos theta line, but
correct.
intersection of -2 and cos theta.
Correct. 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 It is going to lie somewhere here, right? You're absolutely correct. It is going to lie somewhere here. And if we extend this line, right? Okay. Now this is our dr dash. Okay.
Okay.
Got it?
Okay.
So what we do, we again draw a line parallel to this, our real axis. Okay, because still now we haven't plotted our compensator 0 and compensator pole, right?
Yeah.
Where will be placing our compensator 0 and pole? Okay, so what we do next? At this point, what we have to do, we have to find out the sum of angles from poles. Okay, and we have to do it by again using the what do you say, geometrical concept for the graph. And what does it says? Just listen to it. Okay, what it says is that the point dr dash, which is shown over here, it has 2 points. That is, you can see, one is this dr, right, and one is origin, correct? Let me take it as a, let me take this as origin. Okay, and let me extend it here. Okay, so what I'll do, I will join this line and then bisect the angle that is formed by this dr and a, okay, and this dr and o. Do you get it what I said?
Yep.
Okay, so if I draw a bisector here, where I'll get somewhere here. Okay, I'm just drawing it because you need to do it with precision. So, and if I see this angle, what it will be, that I have to measure, and this angle will be 120 degree. Okay, and this angle will be 60 degree. If you'll point it, it will come out to be 60. This will come out to be 120. Okay, and I have to draw the angle bisector. So angle bisector will be coming at what angle? 60 degree,
60.
right?
Yep.
Okay, so now you draw two more lines making an angle of plus minus pi by 2. Okay, so what is 5 by 2? If this is 60, right, what will be this angle? Half of 60 will be 30, right?
Yep.
So 30 divided by 2 will be 15. Actually, this has become a bit like sloppy. I have become sloppy here. Actually, it should be to the mark. Okay, so I'm telling you, just you can note it down and you can draw it and see that sum of angles, if you draw, it will come out to be like uh, 15, 15, and then if you extend it on the real axis and see the poles will be obtained at, see, poles which are there at s equals to 0 and s equals to -2. If you see the angle of contribution, it will come out to be 30°. Okay. And when you mark these lines here, you can see the compensator 0 at -2.75 and -5.25. I'll draw it to the scale and I'll send it in the group. Okay.
Okay,
As
ma'am.
we have already done enough and the time is also over, I'll draw it and send it to the scale. And then I'll send the solution also. Okay.
Okay, ma'am.
I hope you're somewhere today.
We are at home. I mean, is that sorry? I did I get the question right?
Yeah, no, I thought I was saying you are somewhere means you have got some concepts right.
Yeah, yeah, ma'am. There are questions, but I hope that will get answered subsequently.
Yeah, yeah. Because see,